Let's take a look at this problem. The first part is for this given function g, we need to identify x value at which this function is discontinuous. And it is not difficult to see there's a hole here. Therefore, function is discontinuous right at this point when x is equal to 0. So I just type in x equals 0 for this problem. And the second part is to find x value at which g is not differentiable. I would like to quote to a result a summary from the book. So here this summary says f is not differentiable at the point A if one of the following is true. 1. F is not continuous. So if it's not continuous, not differentiable. Second, it has a corner at A at the point. So when there's a corner, it's not differentiable. The third scenario is if there's a vertical tangent line at A, which means vertical asymptote. In the problem that we have, we don't see vertical asymptote, but we do see, hey, there's a corner right here. So when x is equal to -2, this function is not differentiable. Right here, it is not continuous. Discontinuity implies not differentiable. So therefore, we have two answers here. One is -2. The other one is 0. And the last part is to graph g prime. And here, I'm trying to graph the g prime in the same graph. Oftentimes, I would like to begin with where the function is has a horizontal tangent line right here. So therefore, I'm going to put a point here. At the same time, if you look at this point of discontinuity, at this point, if this point is filled, then there should be another horizontal tangent line right here. So this is a candidate. I mean, at this point, the slope is supposed to be 0, but because it's undefined, I should have a hole right here. Now, after I identify these two special points, although this is not defined, I still put a hole here. If it was defined, then it has a horizontal tangent. In this portion, the graph g, the slope of the tangent line is getting flatter and flatter when x is increasing. So the tangent line at this point is steeper than the tangent line at this point, and they're all positive slope. So therefore, I'm gonna say something like that. Okay, at this point, it's steeper, therefore it must be higher, and at this point, it's flatter. So therefore, it must be flatter here, smaller here. That's why I draw a decreasing graph for this branch. Now, on this side, at this point it's flatter, and at this point it's steeper. So therefore, at this point, it should be closer to the x-axis because it's flatter. And at this point, it should be steeper, so therefore it's further away from x-axis. And they're both negative. All, on this branch, they are all negative slope. Therefore, they should be below the x-axis. Now the corner, right at this corner, is not defined. So I'm going to put a circle right here. So its derivative is not defined. Let's now look at the this branch, and compare this branch with this one. These parts, they somewhat similar. At least they're all positive slope right here. Slope of tangent are positive. However, this line is not as steep as this curve, right? So therefore, I think I would do not as steep. That means the slope are not as big as that branch, so it's lower this graph compared to this one is lower. And then at this corner, it's not defined, so I put a circle there. Similarly, for the last part, which is this piece, and kind of same idea as this piece, the orange one, but it's not as steep, so I'm gonna just draw not as steep. The slope, they're smaller in magnitude, so not as big as this branch. So this is pretty much what I would draw. And now let's take a look at the graph here. It looks to us A is matching what we just discussed, right? So I'm gonna pick A. So this is it for this particular problem.